main screen of PEDAS-UD is made up of several key areas. The toolbar contains file management features, basic settings, and report tools. The Object Explorer shows the list of structures and the list of flow paths. The 3D view displays the 3D layout and provides routing tools, drawing tools, and options to turn views on or off. The search panel allows you to search for objects and change their properties in bulk. The move function lets you relocate structures. The calculation results panel and the structure tab allow you to check analysis results and the bill of materials. The property panel shows the attributes of the selected objects. The design result panel allows you to review the final calculation results. In the basic info screen, you can set up project's basic information, the coordinate system, the plant direction, and the mean sea level. Project information is the section where you enter the project name and the model name. Model origin is a reference point inside the model shown as 00, and model origin in unit coordinates is the same point expressed in the unit's coordinate system. Unit origin is the reference point of the unit in the plant coordinate system, and this value becomes the global X and Y used while modeling. HPP elevation is where you enter the mean sea level related to the finishing level. Once the value is set, the pipe invert level in the longitudinal section graph is displayed as an absolute elevation based on sea level, which is useful when checking actual site elevation. The design criteria screen allows you to define the main coefficients and design conditions. You can set the general criteria and the design flow rate, and you can also use the preference value item function to update existing design values for multiple structures at once. Now, I will briefly explain each option. Catchment C is a screen where you manage the runoff coefficient values for each catchment. You can add, modify, and delete the values here. Pipe N is the screen where you manage the roughness coefficient for pipes. You can add, modify, and delete the values here too. Minimum pipe size is the condition used during automatic pipe sizing in automatic calculations. The starting IPECB is the default elevation of the starting pipe or the outlet when designing the drainage network. Minimum cover depth is the minimum soil thickness that must be placed above the pipe. A detailed explanation will be provided later in Other Modeling Convenience Features section. Default slope is the basic slope value applied to pipes, open ditches, and trenches during drainage network design. If you click Apply to all pipe, all existing structures are updated with a new slope. The Firewater Calculation option determines whether the analysis uses rainfall or firewater. This will be explained later in the analysis section. The effective depth is the minimum allowable water depth ratio used for the design of pipes and trenches. Head loss lets you choose which structures will include head loss calculations, and the setting button allows you to enter additional parameters. Velocity is the setting used to define the allowable flow speed for pipes, open ditches, and trenches. Next, let's look at the design flow rate. If you click the Set button, you can see the list of available design codes. If you need additional codes, you can share the reference documents and we will review and add them. Next is the rational formula, and we will discuss it again in detail during the reanalysis section. There are three methods for setting rainfall intensity. Entire area applies the same rain intensity to the entire network. FAA method calculates the time of concentration using FAA rules. TC method calculates the time of concentration individually for each network. If you click the question mark button, you can view the formulas used to calculate TC. If you enable Use Minimum TC, the calculated TC will be replaced with the minimum value when it is smaller than the specific value, such as 10 minutes. The recurrence interval can be selected by choosing a country or region. Currently, only the Talbot equation is provided, but additional methods can be added if needed. Now, let's look at the catchment area screen. This screen defines how the catchment areas are created and how they are analyzed. Width is the maximum allowable width of the catchment. Depth is the maximum allowable depth, and the width times depth is the maximum allowable area, and if this area exceeds this value, the result is marked NG. Distance is the maximum allowed distance from the catchment to the catch basin or drainage point. The surface slope has both maximum and minimum allowable values. For example, a 2.5% slope means the elevation changes 2.5 meters for every 100 meters horizontally. If you enable the option to ignore the min-max rule, the analysis will not apply any limit conditions such as maximum width, maximum depth, maximum area, maximum distance, or maximum and minimum surface slope. HP minus LP is the depth from the ground surface to the top of the catch basin. If you enable Use this value in all catch basin, the same depth value is applied globally. If not, each catch basin uses its own type-based value. The excavation option screen allows you to define how excavation quantities are calculated for each type of structure. If you select one of the structure types at the top, such as catch basin, manhole, pond, pit, pipe, open ditch, or trench, the section view of that structure will appear, and you can set the following items. The paving thickness means the thickness of the surface paving above the structure. Slope is the excavation slope ratio used to represent the excavation in a way that reflects real conditions. A larger slope creates a wider excavation and results in a larger excavation volume. The bottom layers such as lean concrete, crushed stone, or screened can be entered individually according to the design. If you enable the option excluding paving thickness in earthworks, the paving thickness is excluded from the backfill calculation. The type settings allow you to create, edit, delete, and copy standard templates used when modeling structures such as catch basins, manholes, ponds, pits, pipes, open ditches, and trenches. On the left, the template list allows you to add, delete, or copy structure types to build your standard templates. On the right, you can enter the detailed dimensions of the structure. The top cover option is available only for catch basins, manholes, and trenches. DIM is where you enter geometric values such as width, height, and wall thickness. Whenever you change a value, the shape updates immediately in the 3D view, so you can check the structure visually. Design condition is the set of design values that will later be used during analysis, such as optimize or reanalyze. As an additional convenient feature, if you hover the mouse over the dimension field, the corresponding dimension is highlighted in the 3D view, so you can easily identify which part of the structure it refers to. At the bottom, you can turn soil, cover, and dimension on or off to control the level of detail shown in the 3D view. This is useful for a cleaner view or for detailed inspection depending on your needs. You can load a plot plan drawing to model your layout more accurately. Although modeling is possible without a drawing, using one allows you to work more efficiently and precisely. To load a drawing, click the Add button and select the layers you want to display. The selected layers will appear in the main 3D view. There is also a convenient feature for automatically generating catchment areas from the drawing. If the drawing contains catchment information, you can select the layer and set the default runoff coefficient. Then, when you click Generate Catchment Area, the program automatically creates catchment area based on the drawing. If you want to apply a different runoff coefficient to a generated catchment area, you can right-click it and change the value. You can see the generation logic by clicking the question mark button, but since the logic is fixed, the results may not be perfect. If a catchment area is created incorrectly, you can click it with the left mouse button to deselect and then reselect it. After you finish verifying the generated areas, click OK to apply them to the model. When a plot plan is loaded, you can also use the snap function in the 3D view to make modeling easier. However, snapping does not work if the drawing elements are blocks, so if needed, use a drawing with the blocks exploded. You can configure snapping options through the Object Snap menu. Currently, two types of snap are available. Endpoint snap occurs at the start or end of a line. Midpoint snap occurs at the middle of a line. The Foundation Import feature allows you to load foundation structures modeled in PEDAS Foundation into the UD design screen. By bringing in the foundation layout, you can check for interference between UD structures and foundation structures and adjust the layout to avoid conflicts. When you import a foundation file, which is a PEDAS foundation model, the foundation objects appear in 3D on the screen. The imported foundation data is not just for reference. It is actually used during interference checks when designing the drainage network. These interference checks are performed within the optimize function. To design the drainage network, you can select a node type or a linear type and begin modeling. The network drawing buttons are divided into two areas. The upper area contains draw on or off button, and the lower area allows you to switch structure types and select templates. First, here is how to model nodes and linear structures together. When you click on node type to turn draw on, the linear type connected to that node automatically turns on as well. The flow direction is determined in the order you click the points. You can switch to another node type at any time during modeling. You can also model only linear structures. If you select a linear type and turn Draw on, you can create linear structures independently. Let's start by modeling an open ditch. Each time you click, an open ditch segment is created, and the flow direction is set automatically. You can also merge newly created segments with existing ones. If you select a circular point on a corner and double-click or choose Define Bending Type, you can fine-tune the corner geometry. Trench modeling works the same way as open ditches. Next is pipe modeling. Pipes can be connected between nodes or connected directly to catch basins or manholes to receive flow from a catchment. You can also create bending pipes. If you press the B key while a node type is active, you can turn on bending mode. Each click creates a bending point. To finish, press B again to turn bending mode off and place a normal node. For node connectivity, a manhole can connect not only to pipes but also to open ditches and trenches, allowing flow to be passed between different structure types. As an additional convenient feature, if you right-click during modeling, a circular quick menu appears. This menu is arranged clockwise with node at the top, linear on the right, end on the bottom, and bending pipe on or off on the left. If you click the arrow next to the node or linear icon, you can open the list of available structure types and select a template immediately. Bending pipe turns on or off each time you click the icon. Cancel routing ends only the route currently in progress. You can continue modeling from another point. If you right-click again and choose Exit Routing Mode, the entire modeling process stops, just like pressing ESC. If a plot plan is loaded, you can also use snapping to model more easily. There are three types of areas you can create: catchment area, equipment area, and firefighting area. You can create an area by clicking points on the screen, and firefighting area can also be drawn as a circle. Catchment areas can be created in two ways. Catchment area is the basic method where you click points to define the drainage area manually. Catchment area with CB uses the same drawing method but automatically creates a catch basin together with the area. After creating a catchment area, you can right-click and choose Assign Catchment Area to Node to connect it to the catch basin, manhole, open ditch, or trench. When you move your mouse over a structure that can receive the connection, a circular crosshair appears to show that it is assignable. Equipment area allows you to define the footprint of equipment. And the remaining area, after subtracting the equipment footprint, is automatically redistributed to the surrounding catchment area based on the contact ratio. After defining an equipment area and entering the loss value, the connected catchment areas inherit the redistributed area proportionally. When you run Reanalysis, you can see a symbol and a tooltip in the calculation results UD tab showing how the area was divided. Firefighting areas can be created in polygon or circular form. Only the parts of the catchment area that lie within the firefighting area are included in the Firewater calculation. Because firefighting areas overlap catchment areas, you may need to use Select Area when overlap from the right-click menu to select the correct one. In the Property panel, you can also see how much catchment area is included within the firefighting zone. Details about how firewater is calculated will be explained later in Reanalysis section. Next, I will explain the Reanalysis and BOM calculation feature. Reanalysis recalculates the entire drainage network based on the design guidelines set in the design criteria. The updated results are displayed in the Calculation Results tab, and the BOM quantities for each structures are generated at the same time. Any structure that has an issue is marked in red as NG, so problems can be identified immediately. If you want to view all NG results, you can open Search NG. There, you can see the full list, and by right-clicking an item and selecting Zoom to Object, the view moves directly to that structure. Now, I will explain the different rainfall intensity calculation options. When the rational formula is selected in design criteria, an entire area is applied. All networks use the same rainfall intensity value after running reanalysis. Next is the FAA method, which calculates the time of concentration automatically using the C, L, and S values you provide. The calculated TC is then reflected in the recurrence interval settings, which determine the rainfall intensity I. By clicking the Set button, you can choose a country or region to load the appropriate recurrence interval data. The resulting rainfall intensity is applied evenly across all networks. The TC method calculates the TC individually for each network. After that, the selected recurrence interval is used to calculate the rainfall intensity for each network separately. If used minimum TC is enabled, any TC value lower than the specified minimum is replaced by the minimum value during calculation. If you click the question mark icon, you can check the formulas used for each TC method. For the Kirby method or kinematic wave equation, you will also need to set the roughness coefficient n in the pipe settings under surface n. You can apply n values in bulk, and the help section explains the formulas in detail. You can also manually adjust the rainfall intensity for individual networks after calculation. The QO value will be recalculated immediately, and if needed, you can restore the original intensity using ORG value through the right-click menu. When using the TC method, you can assign different recurrence intervals to specific catchment areas. Any area with a modified recurrence interval is marked with a symbol. Next, I will explain how Firewater calculation works. Before calculating fire workflow, you must first choose a Firewater option and the design criteria. Firewater flow for paved area and for maximum fire zone area. Both Firewater flow options follow the same calculation logic, but the input differs depending on whether you use paved area or fire zone area. Here, we will explain it using the paved area method. After selecting this option, you enter two values, Firewater flow and paved area. The Firewater flow value is used directly in QO calculation. Using the two values, the program also calculates the firewater intensity. But this intensity is shown only as reference information and is not used for QO. If you run Reanalysis without drawing a firefighting area, the calculation uses the catchment area as the basis. If a firefighting area is drawn, only the portion within that area is used for firewater calculation. Next, I will explain the option called Discharge Flowing in each catch basin. This method distributes firewater inflow to catch basins based on step-by-step capacity limits. Unlike area-based proportional distribution, this method reflects the actual allowable inflow capacity of each basin. For example, the first catch basin receives up to 2,270 liters per minute. The second receives up to 4,540 liters per minute. And the third receives up to 5,675 liters per minute. And any remaining basins each receive 946 liters per minute repeatedly. The max quantity value sets the upper limit for the total inflow. The combined capacity of all catch basins cannot exceed this amount. Anything beyond the max quantity is not distributed further. We will now demonstrate how this firewater calculation method works. Now, I will explain the option Input the fire design flow for each catchment. This option lets you manually enter the firewater design flow for each catchment area. Only the values you enter are used for the calculation, and any existing firefighting areas are ignored. A symbol will appear next to each catchment area where QO has been entered. Next, I will describe the option Input the design flow for the fire area. With this method, you first draw a fire area and then enter the firewater flow value for that area. The program automatically distributes this flow to the underlying catchment area based on area ratios and calculation rules. You can view the distributed values by selecting the fire area and checking its property panel. Finally, let's look at a few additional functions available during reanalysis. If a pipe is connected from a pond to a manhole, you can manually enter the QO value for the pond. After running reanalysis, the downstream pipe will reflect the updated QO. Normally, pipes allow only downward gravity flow. However, if a pump is placed inside a pit, you can change the pipe's inlet and outlet elevation to create an upward flow system. To do this, adjust the outlet elevation and apply a negative slope. For open ditches, you can also specify the points where Q is calculated. By default, Q is determined using the depth at the last point. If you right-click a point and choose Set Q Calculation Point, the calculation uses that position. To return to the default, select Set Q Default Endpoint. The additional input feature is used when extra inflow must be considered. In a node's additional input section, you can enter a value equal to the catchment area multiplied by the runoff coefficient. After reanalysis, this value is included in the QO calculation and marked with a symbol. Next, I will explain how the optimize function works. The optimize feature automatically analyzes the drainage network and adjusts the sizes of structures and their connections to the most appropriate configuration. Let's begin with the automatic pipe sizing process. When you click the question mark icon, you can see the calculation logic used to determine the new pipe diameter. For example, if you look at pipe number 8, its current diameter is set to 300. Once you press the Start button, the program begins searching for the optimal diameter, and once the calculation is complete, you can see that the diameter has been updated to 600. If you open the log window, you can check exactly how the diameter was determined. The program starts from the minimum pipe size defined in the design criteria, such as 2 inches, which is 50.8 millimeters, and then increases the diameter in 2 mm increments. For each size, the program checks whether conditions like velocity limits and the QO over Q ratio are satisfied. Once the program finds a size that meets all the criteria, it automatically replaces the pipe with the closest matching template size. The sizing process for open ditches work in the same way. Next is the sizing process for catch basins and manholes. This function looks at the maximum inside height defined in the type settings and compares it with the actual inside height of each node. Based on this comparison, the program automatically switches the node to the most appropriate standard template. Next, I will explain the inlet and outlet reconfiguration feature. When multiple pipes merge from different directions or the modeling sequence is mixed, the IPE levels may end up misaligned. This feature reloads the inlet and outlet elevation values in the correct order based on the actual flow direction. However, if you manually edit the inlet or outlet value of a pipe, that pipe will not be reordered automatically. Pipes with manual edits are displayed in green, so you can easily identify them. Finally, there is the interference check function. This function automatically checks whether any UD structures are interfering with each other. If an interference is detected, the affected structures are highlighted in red so you can relocate them immediately. Once you find the conflict, you can use the move function to adjust the position of the structure and resolve the issue. Next, I will explain the different outputs that can be generated. The system provides several types of deliverables, including the calculation report, the BOM, the drainage plan DWG, the manhole and catch basin schedule DWG, and the longitudinal section graph. You can open the calculation report either by clicking the Calc Report button at the top menu or by right-clicking in the calculation section of the list view at the bottom. The report is organized into pipe, open ditch, and trench tabs. After selecting the structures you want to include, you can export the report into Excel or PDF. The BOM report allows you to review the quantities for either all structures or selected ones. It includes 3 sheets, a summary of major quantities, quantities organized by standard template, and a detailed breakdown for each individual structure. This makes it easy to check all required material information. For the drainage plan DWG, you can toggle catchment area visibility on and off. The manhole and catch basin schedule DWG displays detailed information for each structure. The longitudinal section graph can be created by using Select Up or Downstream for longitudinal section graph in the Routing tab, or by selecting a structure in the 3D view and calling the Up or Downstream function. Once the related structures appear at the bottom, you can press the longitudinal section graph button to generate the drawing. Additionally, when using a mouse right-click menu, you can perform batch property changes or optimization on only the structures that are currently visible. For more details on these features, you can refer to the final section of this video. Now, I will explain how the PBS block feature works. PBS blocks allow you to categorize structures according to PBS or unit areas so that you can easily view structures and outputs on a unit-by-unit basis. To use this feature, first right-click inside the PBS list and create a new PBS unit. You can also assign a unique color to each block. You can define each unit area using either the polygon mode or the rectangle mode. If you draw an area using a rectangle mode, the Assign to PBS window will automatically appear, and you can select the unit to apply to that area. All structures inside the drawn area will then be assigned to that unit. There is also a convenient feature called Clone Temp Block. This allows you to copy the selected area in any direction, which is useful when you need to create multiple unit areas quickly. After cloning, you can assign the new areas to their proper units. If you close the Assign to PBS window by mistake after drawing a block, you can simply select the area again, right-click, and choose Assign to PBS to map it manually. You can easily edit unit boundaries by selecting a line and using Add Point to insert intermediate points. This lets you reshape the area however you need. For more precise adjustments, you can also modify area positions or point coordinates directly from the panel at the bottom left. Once PBS assignment is complete, you can go to the main Object Explorer and select any unit. By choosing Show in New tab, you can view all structures belonging to that unit in a separate tab and check their related outputs independently. Next, I will explain several additional modeling convenience features that can help you work more efficiently during the design process. In the main 3D view, you can use the ortho mode, which allows you to work in strict horizontal and vertical directions when designing catch basins, manholes, or catchment areas. There is also an auto spacing feature, which automatically generates structures at fixed intervals. To use it, you simply enter the spacing value in the automatic spacing settings and turn the feature on. Once activated, any newly created structures will follow the spacing you specified. For moving structures, you can use the Move function located at the bottom left. This allows you to move multiple structures at once. You can also hold the Shift key and drag and drop structures directly in the 3D view for quick repositioning. There is also a ruler tool, which helps you measure distance between structures or between catchment areas. When you click the ruler button, two buttons appear. You can measure by selecting a from point to a to point, and you can clear all distance markers using Clear All Distance tag. When measuring nodes, you can choose whether the distance is measured from the top, the center, or the bottom of the node. For linear structures such as pipes, open ditches, and trenches, the top means the first point, the center is the midpoint, and the bottom is the last point. You can also use the click point option to simply click 2 points in the view to measure the distance between them. The search function allows you to easily find structures that meet specific criteria and update their properties in bulk. You first choose the type of object you want to search for, then set the condition you want to use. You can search for objects that are equal to, not equal to, greater than or equal to, less than, or less than or equal to the value you input. After the search result appears, you can select the ones you want to change their type or other properties all at once. There is also a minimum cover depth feature that prevents pipes from being exposed above nodes when the downstream pipe diameter becomes larger. You can set the minimum cover depth value in the design criteria, which defines the minimum amount of soil that should cover a pipe. This value is applied automatically to newly modeled structures, but for existing structures, you must press the Apply button to apply the setting. The renumbering feature allows you to reorganize or modify structure names in bulk. You can access it by right-clicking the main 3D view and choosing Renumbering. If you have structures selected, only those will be renumbered. In the Renumbering window, you can set the item type, order type, and option type. You can also specify the starting number, the number of digits, and the separator between the item name and the number. After applying the renumbering, you can manually adjust individual names in the after name column if needed. You can also change properties or run optimize only on selected objects. There are two ways to do this. You can select objects in the 3D view and right-click to choose Optimize for selected items or Change property for selected items. Or, in the Routing tab, you can use the Select Up or Downstream function, then right-click the list at the bottom to access those same options. When you choose Optimize for selected items, the selected structures appear at the top, and you can choose which optimization tasks to run. When you choose Change Property for selected items, the structures are shown by category, and you can edit only the attributes that are allowed for that category. For example, for catch basins, you can update the type name or the rotation value, and the changes will apply to all connected structures. Lastly, you can edit catchment areas using the Edit Catchment Area feature. When you right-click a catchment area and choose this option, an editing window opens. Here, you can freely reshape the area. Tools like Cut Point to Point allow you to divide an area using 2 points. While Cut Draw Line lets you draw a cutting line by hand. If you want to combine divided areas back into one, you can use the Merge function. You can also reset the area to its original state or turn plot plan layers on and off for reference during editing. You can add additional points by right-clicking the boundary and choosing Add Point. This allows you to fine-tune the shape by dragging the new points. If multiple catchment areas overlap at the same point, moving a shared point might move more than one area. In that case, you can select the specific catchment area you want to edit first, and then move the point so that only the chosen area is adjusted.